What if your sparse matrix has widely different numbers of non-zeros per row? We'll explore the Jagged Diagonal Storage, or JDS format, which handles this, keeping efficiency without wasting memory. So let's bring in a matrix so that we could examine this. Formats like ELL or L require all rows to be padded to the same width. This is great for GPUs, but it's wasteful for memory, especially when the distribution of non-zeros is uneven. JDS avoids this by storing only what's needed and aligning the non-zeros diagonally to maximize the memory efficiency. So the first step is similar to L. We extract all of the non-zeros per each row, as well as their column index. So I'll have value here and call IDX here. So let me get the call index for the first row. And since we've done this before with L, I'll quickly fill out the remainder. At this point, this is where it differs from L. Now we sort the rows in descending order. This lets us align the longest rows first, and it minimizes the empty padding. So let's label our rows 0, 1, 2, 3, 4, and 5. And let's iteratively select the largest and move it to the top. After looking at this, we realize that row 1 is the largest, so we'll move it to the top. Followed by row 1 is row 3 and 5 respectively, so we'll move these to the top. And the remainder, 2, 4, and 0 are already correctly sorted. Now, we reorder the matrix into an array according to this sorted order, and we also keep track of where each row starts. Similarly, we transpose this view as we done in L, grouping the first element of every row, followed by the second and then the third. It would follow a pattern like this. Hence the name Jagged Diagonal. So I'll copy these to keep track of the permutations. This is just the order of the rows that were switched so that we can rebuild the matrix later if needed. I'll call this the permutation array. Now, let me store these in column major as done in L. And I'll also keep another element, call the iteration pointer, that keeps track of where each iteration starts. And since we have 1, 2, 3, 4 is the maximum non-zeros, our iteration pointer will be 5 elements long. So let me extract the first column. The first iteration starts at 0. And the next begins at 6. And again, the last entry of the iteration pointer keeps track of all the elements in the array so that we can determine which threads will be running for a given iteration. Now I'll quickly do the same for value. Now let's consider what happens when we add a non-zero to the array. There are two cases. For example, let's consider the case where we add a non-zero to row 0. So I'll add a Z in column 2 of row 0. As you can see, our reordering won't change. So our intermediate structure remains the same, we just append. However, similar to CSR, we will need to shift elements right and increment the pointers. However, if adding an element, say adding an element adding an additional element to row 5, this would cause our intermediate structures to be incorrect and would require resorting. This reorting ensures our diagonals remain tight so that there is no wasted space and no extra padding. So it has greater memory efficiency, but modifying it is more expensive than both COO and CSR.